Hello, my name is Rusty Bowers. I'm a high school math teacher at Belgrade High School. I've got 7 years experience and just wanted to share some insight and a pathway that I have discovered through my master's at NSU and just my classroom experience in kind of creating my own path. And then at Belgrade, we're also going away from the traditional pathway of mathematics and building our own integrated math course, which this is what this idea is on transformational geometry and its connection to algebra. Really, I think that this is integrated mathematics. So, in this video, I just want to share with you some ideas that I have for this. It's kind of hard to set up some things to display for you to show you my ideas and kind of a whole rounded concept the best that I can without boring you and making this video, hours long. But that could easily happen. So, anyways, I'm going to try to go fast and kind of do a little bit of a shotgun approach in the sense of sharing some ideas and concepts with you. But I'll try to stay on this kind of concept flow. These are some notes that I had made up to kind of get an integrated math concept for myself, and I thought instead of typing it or whatever, I would just show it in my video. I start teaching math, really, I think we should start with the properties of our three rigid transformations. Dilations are in there too, but it's important, I think, for us to really understand that the properties that always occur when these transformations are performed actually help us create our geometry world that we explain in a horrible way in our geometry textbook. So I'm going to talk about the transformations, and then I'm going to connect, as I'm talking, the logic and congruence concepts that we can actually hit while we're talking about all these transformations. Circles and radii, perpendicular lines and bisectors, connecting concept to kites and rhombuses. I'll show you a special quad GeoGebra app that I have. By the way, I don't know if I just said this at the beginning or not. I love GeoGebra. I learned it in my undergrad at MSU. We used it throughout my master's, and now everything that I do and everything that I envision is always through GeoGebra. And I got to the point where I'm pretty fluent with it, and I can pretty much make any app that I want, which is awesome. GeoGebra is an incredible program. So that's really what this video, I'm going to be showing you these kind of concepts using GeoGebra. Okay, so what I'm going to first do is talk about these transformations and then show you how we can connect those transformations to parent functions in algebra, tables, graphs, equations, ordered pairs, those representations that we use, how they can help us go to inverse graphs and looking at functions or non-functions. Like if you rotate a parabola 90 degrees around the origin, we get a non-function path. Okay. Also, using our generalization rules that we use when we perform our transformations on a coordinate plane, we can use those to help us generalize our vertex form of a function. So I have some more notes here too, and I'll hit these up in a little bit, but let's start with that concept, kind of talk about the transformations and then connect it to some algebra. So the first one that I wanted to show you is just kind of this little app I made for a little demo of our transformations. We've got the three rigid and we have a non-rigid transformation here. Right now I got rotation selected. With rotations, we need a center of rotation, which in GeoGebra here, we can just move that point around. And I have a slider here that changes our angle of rotation. So when I rotate this baby, it's going to go ahead and rotate. It goes in a clockwise direction for positive. But the properties in rotations that I use is this idea of take a point. Maybe I'm going to make this stand out here. I'll make it this light blue color, make it a little bit bigger here. So if I take a key point on Mr. Incredible here, maybe like his foot. I'm going to put a blue point on his foot. There's some different logic that we could play around with. In this case, we have a pre-image and a center of rotation. It's getting rotated 255 degrees to end up here. Okay, so really what I want my students to understand is the distance from the pre-image point to the center of rotation is preserved, and to measure that we use circles, a construction concept, and we can see that this point right here must be the rotated point, which, depending on how you want to use these apps and teach your lessons, I mean, you could go multiple paths in using these. But right now I'm just going to show the rotate tool here. So it's rotate object around point by angle. So I'm just going to click on my point that I want to rotate. Oops. Let me clear that. Okay, so now I'm going to grab my rotation tool. I'm going to click on the point I want to rotate, the center I want to rotate around, and the angle that I want to rotate. Either I can type the static 255 degrees if I want to, or I can use this little box here, grab my alpha, which is the angle, and now whatever alpha is, that point will rotate as well. And notice it rotated to that point there. We've got radii of the same circle, hence distance is preserved when we rotate. And so now we can kind of see that as we rotate this, and I used alpha to rotate that point follows a circular path, and so does every point. Let's say, for instance, I want to grab another one really quick, and maybe I'll make it a dark green, and I want it to be somewhere maybe right on the eye part here. Okay, so now what I want to do is the exact same thing. I'm going to grab my rotate tool. I'm going to rotate this point around our center. Maybe. Rotate this point around the center, and I want it to go the same angle, alpha. So there's our point that pops up there on Mr. Incredible. And now another cool thing with GeoGebra, maybe I want to show its path as I rotate. So I'm going to right click my rotated point, and I'm going to turn trace on. And now when I rotate Mr. Incredible around, that path, that rotated point, is getting traced. It's showing its path here, and we can see that it follows a nice circular path. So those are just some properties that I like to talk about with rotations. Okay, let's talk about reflections. I'm going to refresh my view and clean that up. So I'm going to show reflection, oops, and those points that I made. Sorry, I didn't plan for this part here. I'm just going to delete a couple things. Okay, so we're back here. Now when we talk reflections, so when we reflect, we need a line of reflection. I went ahead and made the reflected object already. So as this line moves, we can see the reflected image move, but it's the same idea, is that we can grab a pre-image point, maybe right on his teeth here, and then I'm going to reflect this point over the line. So I'm going to grab my reflect tool. I'm going to take this point and I'm going to reflect it over our line of reflection, and we can see this point pop up right here. I hope that green shows up in the video. But now what I like to show is our properties of reflections. The distance the pre-image is from the line of reflection is equidistant to the distance the image point is, and the segment and the line of reflection are perpendicular to each other. So if I grab my angle tool, I just got to put a couple extra points here, so that if I grab my angle tool, I can measure this angle now and see that it's 90 degrees. So those are the two properties of reflections. We have equidistant and we have perpendicular, which allows us then to talk about isosceles triangles and their properties as well. So what's cool about this is if I want to maybe hide my objects, I don't know why I made this app a while ago, and I'm not sure why it doesn't want to hide on me. But anyways, imagine it's gone. Sorry, maybe I'll just move this out of the way. 11 videos go smooth, huh? Okay, there it is. Sorry. So let's pretend that that's not even there. Now, when we talk isosceles triangles, we could talk about the perpendicular bisector theorem, that any point on a perpendicular bisector is going to be equidistant to the endpoints of the segment. So there's an isosceles triangle. We've got the perpendicular, and we have the height going through the vertex. We have congruent triangles within here. So we can see reflection properties kind of open a doorway pretty much to our world of geometry. Okay, oops. The next thing that I want to show you is translation, sorry. down here, and again, I don't know if you can see this in the video here, I have the vertical and the horizontal components of our vector shown here, and it makes a right triangle, which is definitely huge. As I change this vector, it's changing how we translate Mr. Incredible. So we can talk about how the distance between 2 points, or we can get direction involved of how an object moves. Okay, so translations, Pythagorean theorem, distance formula, all that good stuff, similarity. And slope, really. I mean, the thing too that we talk about with translations and moving a point is a point has to move vertically and or horizontally when it moves diagonally here. So to find that, we just find the vertical difference between the points and the horizontal. Slope is the exact same thing. We just take those numbers and we look at it and we compare them in a different manner by making a ratio that describes how a line's behaving. Okay, and then dilations, just to show you as well. I have a dilation here. So now when I move my center of dilation, we can kind of see if I want to make a bigger image, maybe I want to make my scale factor bigger then. Okay, so there's our dilation. We can talk all sorts of good proportions and getting some similarity in there. Okay, to even clean it up a little bit better, to show you some geometry, I have another dilation, same idea, it's just now vectors and shapes. So as I change my scale factor, with this being the pre-image, then we can see that we can grow and we can shrink. And there's a nice similarity in proportions involved there. Okay, you can kind of also see a three-dimensional look here, which can get us into talking about maybe volume or surface area and whatnot, as you know, kind of a calculus idea, integrals or pieces getting dilated to a point. The possibilities are pretty unlimited here. Okay, so the logic that I wanted to share too in our integrated mathematics is, this is what I think the connecting factor between geometry and algebra truly is. I'm going to ask a question here. What is the relationship between these lines? Meaning, are they parallel, perpendicular, or neither? A typical math question we ask. So just to show you the logic that we use, right now we have a blank plane, which allows us to use our geometry concepts of construction. They look perpendicular to me, so I'm going to check it using geometry. So I'm just going to put a couple points on both lines. Okay, so now all that I'm going to do is I'm going to make a circle. I'm going to change its color because I'm going to have two circles here. I'm going to maybe make this one green. And all that I'm going to do is center a circle at C. And maybe I'll go out to D, just to make a point there. I'm going to grab another circle and I'm going to change its color. Maybe I'm going to make this one purple. Oh, maybe that one purple. I'm going to center my next circle at D, and maybe I'll go to this point right there, right? So using, and we've already talked constructions at this point of how to construct perpendicular lines, but to verify that they're perpendicular, we now have a perpendicular line construction, which is a connection then to our special right triangles. I want to make this a different color. Okay, green. So now I'm going to make green segments to show radii of this circle. So in this green circle, centered at D here, I'm going to make two radii where these circles intersect. So if I connect the segment D to this intersection, and then D to this intersection, which is where our perpendicular line falls if we're comparing to the blue line, we can see two radii of that circle, and they have to be congruent because they are radii of the same circle. And now I'm going to do the exact same thing over here. I centered this purple circle around C, so I'm going to make a radius on this one, and I'm going to make it purple, and another radius as well. And we can see in this construction, what this construction is really making is a kite. And students know kites, they just don't know how to analyze it and look at the properties and all that, and that's what we have to teach. But they know what a kite is, and they should know that these two segments are congruent, and these are too. We use circles and construction logic to really argue why. And now we can look at those properties. We know in kites diagonals are perpendicular. So that helps us geometrically then prove that two lines are perpendicular. Okay, so that's just an idea of how geometry helps us with logic. So now the next thing that I want to do is, let's put this on a coordinate plane. Let's put scale to it, put some numbers to it. And now this is where algebra comes into play. Now that we have numbers, our students need to learn how to use them in the way that we do. Maybe I want to find the slope of this line so it looks like it's a -1/2, and the slope of this line here, it looks like it's a +2, and that's our opposite reciprocal relationship. So we can see that these are perpendicular using an algebraic approach as well, but appreciating the difference between how to logically prove perpendicular via geometry concepts in construction and algebra concepts in scale. Okay, so the next thing I wanted to share with you is transforming parent functions, or any function really. So I created this app here that has reflections, rotations, translations, and our main 4 reflections over the x-axis, y-axis, y equals x line, y equals -x line. We can also rotate 90, 180, 270, or what I call -90, and we can translate functions as well. So if I wanted to, for instance, I could reflect this line over the x-axis, which kind of looks like a y-axis as well, but I also make the line of reflection show up. Maybe let's take a function that's not as symmetrical. That didn't do it either, but let's translate this one to the, or 2 to the left maybe. Let's do that. X plus 2 cubed. Oh, that didn't really help much, but we moved it around, kind of show you that you can enter any function you want to. The function will come up black, and in this case, green, reflect over the x-axis. Here's what we get. Okay? Maybe we want to reflect it over the y-axis. So now if we reflect this function over the y-axis, here's what we get as well. In this app, I only have data using this, you can see in the spreadsheet. These are my inputs going from 0 to 4. So maybe the x cubed is a little too big. Let's just do, well, x squared. Okay, so with parabolas being symmetrical about the y-axis, when you reflect this thing, you can see that the reflection then, and I also show the reflected points of these ones, they just show up on the parabola as well, hence the reflective symmetrical nature of a parabola. If we reflect it over the y equals x line, which is our inverse line that we will reflect, we can see our inverse graph here. And we can see it's not a function, but we can see this connection when we generalize that this point here is at 4, 2, and we just switch the x and the y coordinates. When I made this too, by the way, if you look at this spreadsheet as I kind of zoom or go around, there's all these points based off of our parent points. And each color represents each one of these transformations. So I'm just using those generalizations where if you have an ordered pair, maybe when we reflect over the y-axis, all we do is we just flip the x coordinate and keep the y the same. And that's exactly what I did here to make this app. Okay, so kind of a cool idea here. We can rotate if we want to, and I also show angle of rotation as well. Maybe we want to rotate 90 degrees. Ooh, that looks the same thing as if we reflect over the y equals -x line. Okay, so all sorts of fun concepts there. But that builds us into building our vertex form of a function. So that's what this is here. So let's say this app, and again, I'm sorry if I'm going fast and this is overwhelming. I'm trying not to make this video too long and share with you a whole lot of ideas, I guess. So hopefully, there's follow-up and I can share my thoughts even better. But this app that I made, we can graph linear, quadratic, absolute value, and exponential functions, and I believe they're just the parent functions when you click on these. So we can actually talk about parameters if we have our vertex form of a line. So I got to show algebra work. If you want to see the algebra side, the generalization, and how the a, the h, and the k that we're using is transforming this graph around. So kids will learn that if we want to slide horizontally, that's going to be our h variable, and we can see how that affects our equation here. Okay, if we wanted to maybe go vertically as well, we can adjust our k value, and we can see an equation getting formed here. And we can just match this to input and output, like check it. If we put in a 5 into this, do we really get out negative whatever that is? Okay, but we could do that kind of analysis as well. We can change our scale factor around here, and we can make it flip upside down, and all that good stuff. So all that really is a nice conversation using our transformations. We can translate, we can reflect. Rotation doesn't typically come up in these conversations, but the other two do big time. Okay, so now back to this kind of layout. Those are just kind of talking about the transformations, how we use construction and logic for geometry. Algebra is just generalizing patterns, but also, like I said, I think a huge connection is putting a grid and an axis so that we get scale. And now we can use scale to help with numbers. We transform any parent function we want to. I only showed you a couple. You could do absolute value, exponential, anything really, any kind of root function. Tables, graphs, equations, ordered pairs. There is a nice connection. The tables are just spreadsheets in GeoGebra. Generalizations help me create that app, and we can show kids that as well. Graphs obviously are huge. Equations, ordered pairs help us graph. Okay, let's go into some other geometry ideas here, like maybe area of special quadrilaterals, for instance. So I have an app for that too. This is one that I made. These little symbols are custom tools, and these are each one of our special quadrilaterals. So for instance, let's say that we wanted to find the area formula for a rhombus. So for my rhombus app or tool here, all I have to do is click 2 points, and now I have a rhombus. Okay, so if we want to find the area formula for this, I really want my students to understand symmetry. So lines of reflection, which really, if we just look at the segments inside, those are our diagonals. But now we can see congruent triangles in here, right? So we have 4 congruent triangles, and that can be argued out. But now when we talk about area, the area formula that our students know really is that the area of a rectangle is length times width. I'm writing with my mouse, sorry. Length times width. So let's use that formula to help us reason the area of this rhombus. So to do that, what I'm going to do is use my polygon tool, and I'm going to create 4 individual polygons that are these triangles. Okay, maybe I'll make them different colors too. I'm a color coordinated kind of person. Okay, so this second one here, I'm just going to try not to make this too long. Oops. So now let's go boom. Okay, make this one say red, and then we've got this, 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 this. Make this one blue, and then could have just went off my side wings, huh? Colors. So let's see, purple maybe, or orange. Okay, so we have these 4 different colors. We again argue that they're all congruent in shape and same area. Okay, but now when we think about making a rectangle out of this, the reason that I wanted those polygons is because now I'm going to rotate these triangles 180 degrees. And through discovery, kids will say maybe reflect. But if we reflect this, we may or may not make a rectangle. Maybe we do, but not on all shapes. So I'm going to grab my midpoint tool, and I'm actually going to just have GeoGebra find the midpoint for me, which is right here. And now I'm going to grab my rotate 180 degrees tool. I'm going to rotate this, or at this point, 180 degrees. So there's a rectangle that gets formed here. And I'm just going to follow that idea here and rotate these other 3 areas the same manner. And now we have a rectangle. And we argue that when we rotate these 90-degree angles inside here, they rotate out to make a rectangle. So we could prove, one, that it's a rectangle. But now we can see that the area here is just going to be this diagonal length. That's really the length of the rectangle, times this diagonal length, which is like the width or the other dimension. So we have the length times the width, diagonal 1 times diagonal 2. But we can see that that area is going to give us twice as much as what we want. So if we just cut that in half, we will have the area of this rhombus. So that's going to be true no matter what our rhombus looks like. There's so many points here, I don't think I can move it. So anyways, that's an example. That's just a rhombus, but we can do that same concept. Take any of these special quadrilaterals and transform them to make a rectangle, and we can use that rectangle concept, this area equals length times width, to reason with our special quads. Okay, sticking with area, I just want to show a demonstration of how we can use GeoGebra maybe to help us with the area of a circle formula. So what I did was I created a circle, and I have three different sectors here. And what I did was I took these sectors and I just translated them so that we get this pattern where we take one piece and we just put the next piece next to it, where we flip it and we can see the curve on top, curve on the bottom, next piece has curve on top, the next piece has curve on the bottom, and so forth. So when we continue that out, in this slider it changes the number of sections that we have. We can just see how these little sectors, if we continue that pattern here, starts to create this nice elongated shape. Sorry, I'm going to try to see if I can fix these so they don't move on me. Shoot, won't let me. Well, anyways, the idea here, and a good conversation to have with students is, don't start falling apart, GeoGebra. Okay, well, the idea here is that if we have multiple sections, more and more and more and more and more, like maybe 40, we can see that the little slices of our pie or whatever are getting smaller, and therefore the curve, the dramatic curve, is actually straightening out a little bit. So as we talk about approaching like infinity, for instance, I got this to go up to 200. I'm sure it can go up more, but what happens is, if they understand the idea, that all those little pie pieces are just getting placed to make an array here, which makes a rectangle. And then we can see there's a good talk about, are these pieces still curved or are they straight? So I'm going to zoom in GeoGebra here. Zoom in, zoom in, zoom in. And I had those lines in that circle for a reason as a gauge here. And you can see as we zoom in closer and closer and closer, now we can kind of see that line that I had drawn, and we can just see the difference between that line and the curve of our circle still. So there's really a difference in that curve and the line. But the idea is, what if we cut up that circle into more slices and continued, like 1 million of them, or 10 million, then the difference between the curve and this line will get smaller and smaller and smaller, because the distance between our points up here are now getting smaller and smaller and smaller. What if we had an infinite amount? And that's really the idea behind the area of this circle. If we put it in an array like this with an infinite amount of pieces, we actually create a rectangle. So then if it's a rectangle, we argue that we still have the area of a rectangle being length times width, but the length here in this case, or the height, whatever you want to call it, is the radius of the circle. And because of taking a part of the circumference on top, and then we move the next one on bottom, then on top, then on bottom, then really each side here has half of our circumference, which would just be like pi r squared. Here is r, so we have r, our radius, times pi times our radius, or pi r squared. So one example of using area of a rectangle to help us argue the area of a circle using GeoGebra. Okay. Pythagorean's theorem, for instance. What I find interesting is Pythagorean's theorem really just says is that if we make similar areas based off of our sides here, then the area of the two smaller figures will add up to the area of the larger one. That's really what its theorem says. We use squares, and I talk to my students of why we use squares after we compare. Like, I made this app, areas of circles and equilateral triangles, but we can change this triangle however we want to using the demonstration of Pythagorean's theorem. We can see our nice formula here that if we have a side length squared, that's the area of this green square, side length squared, area of this blue one, and I give the area 2 and 10, so if we add those up, the area of this square will be 12, therefore the side length is going to be the square root of that area. So we know that this is going to be the square root of 12, this hypotenuse. It's also true if we use, say, circles, for instance. So the area of the smaller circle and the area of the other smaller circle, we add those two areas up like I show here, then they're actually going to equal the area of the larger circle, the orange one. Okay, so using area concepts and in a different way in the dynamic features of GeoGebra, students can see these relationships better and understand what this formula, I think, is really saying as well. Okay, and then the last thing that I just want to share is evaluating functions. I know that my students have a hard time understanding equations of, say, a line and evaluating, like really understanding the concept of what we're doing here. So what I did was I created a linear pattern generator just using integers as inputs for right now. So you can change the y-intercept value, so just notice, like if I set it to 6, here's our y-intercept at 6. The difference, when I made this up, we're coming out of sequence talk, call it M for slope if you want to, but the difference or slope we can adjust. You know, you can talk about, 2 points make a line, so if I want to actually model this pattern with a line, then all I have to do is grab my line tool. I just need to make 2 points, and a good question is, which points do I go through? Same idea when we talk about finding, evaluating functions. It doesn't matter if I put in, say, a 4 and get out, it looks like a 13, and I put in -2 and it looks like I get out 2 and something. I'm not quite sure what that is. Maybe 3. Looks like it's less. But if I click on that, it creates a line and collects all those collinear points. So now, let's evaluate. So this n here changes what number we want to evaluate at. So if I show this n t of n, again, sequence notation, but I could say like n f of n, or n whatever, output of n. I keep having my tool out. Then if I click on this little box here, what it does is it shows some nice vectors here. So my students understand that this is our input axis, the x-axis, aka input axis. This y-axis is our output axis. So if we put in a 3, looks like we were going to get out an 11. Okay. If we put in that -2, for instance, no, +2, -2, and I have these boxes too because the sliders are a little clunky sometimes, but you can also just type in these boxes. If n is -2, we can see the output is looks like 2 1/4, maybe 2 1/2 somewhere, because 3 is right in the middle. Okay, you could ask, what's the equation of this, or like what I did, I have the algebra here to show it. But what I want students to understand is with this algebra work here, where this could be mx plus b, dn plus b, doesn't matter. This is just sequence notation that I made. But what it's really showing us here is that, we know our slope, we're going to evaluate -2, and we add that to our y-intercept value, and we crunch it through. But kids get lost in all that. And I think that this does a really good job demonstrating what the rule is really doing. Maybe I'm going to change our slope to 1.5. Okay, so what I have here is this third checkbox, which is actually illustrating the rule, okay? So when I click on this, some vectors are going to pop up. And with this example, since we're evaluating at -2, and our slope is 1.5, our y-intercept is 6, what this rule is really saying is take your y-intercept value, this b value, right, which is 6, and I'm illustrating it with a vector showing from 0 to 6. And then our number that we're evaluating at can just be a multiple of our slope vector. And since we're going negative, we have to understand that negative flips direction. So instead of going up the +1.5, because we're going negative, we're going to go down 1.5. So from the 6, if we go to the left 1, to get to -2, we have to go to left 1, and we go down 1.5. We have to go left 1 more. Now we're at -2, and we have to go down 1 more, 1.5. So on the y-axis here, we can see how this output, where it comes from by taking the y-intercept of 6 and apply our difference of 1.5 -2 times, or just flipping the direction. So now we're going down 1.5 and 1.5. Maybe you want to evaluate, say, at 6. Okay, so now we have our y-intercept here at 6, and now we apply our difference, or our slope, 6 times, since we're evaluating 6. So if we have our 6 and we add 1.5 6 times, we get up to a total of 15, which is also, again, shown just by this input-output after a while. But really, I think it does a good job demonstrating how this equation is really creating our output values, and it's giving us that nice function kind of thought here. Just initial value, apply our difference to get us to that point however many times we need to. All right, so I hope that that wasn't too confusing, or I hope that I'm onto something here, but if it makes you curious about how we can teach mathematics differently, in my opinion, if we're talking about our transformations, there can be a connection to really anything in mathematics that we want to. And these are just some ideas that we can do. And I think, too, the trigonometry is just an easy conversation that we can do rotations. There's a nice path, I think, between trig and slope, and combining angles and slope. We can do that pretty well, I think, through this kind of conversation. So I hope that that makes sense, and I hope it entertains you. Please feel free to contact me at rbowers@belgradeschools.com. Maybe I'll just type that here if you need it. rbowers@belgradeschools.com. Email me there and with any questions or whatnot. So anyways, thank you for your time.